and welcome. In this module, we will first review some concepts from signals and representation of digital signals, or rather signals as vectors, and we will talk about concepts such as signal space. This is important because we are going to study digital communications, and digital communications would involve us to learn about constellations, and these constellations are coming from these signals as signals as being thought of as vectors. This is what is sometimes called as the geometric approach to signals, understanding signals, and that is very valuable and widely used in analysis of digital communication systems. And that is important for us in the optical communication systems, because much of optical communications today, in fact 99% of the optical communications today happens in the digital communication format, in the sense that we only almost have digital optical communication systems. So, to understand those concepts, we will have to review some fundamentals. Let us begin by very briefly recalling what a signal is and then talking about its Fourier transform. Okay. So, a signal, we have been talking about time varying waveforms, and a signal is essentially a time varying waveform. Okay. Suppose S is a mapping that I take. So, I have a variable called time. So, at each time I might have some amplitude or I might have some value, it could be power as well. So, all these values can be captured by writing this as S of t. So, S of t would represent two notations. One, it would give me the value of this particular function, which would be defined by S of t at the time t. It would also give me how the function itself is changing. So, it is kind of slightly two related notations which we are compressing by saying that S of t is a signal. This signal is continuous signal because time t can vary continuously. There is a different signal called as a discrete time signal, in which case time can take on only certain samples. Okay. This is coming from the time domain, but in fact you can also have discrete signals in a various other contexts. For example, you are playing cricket, the number of the numbers that you score against each ball, right, would be an example of a discrete time signal, right. So, you can have discrete time signals coming not only as a time dependent thing, a discrete signal coming not only in terms of the time, but it can also be a function of anything else. For example, you take a picture that would correspond to a two-dimensional discrete signal, with each variable being the pixel point, and the corresponding intensity of the picture would be the discrete signal there. It would be a 2D signal. We will mostly be dealing with only one dimensional signal, in the sense that we will have only one independent variable and the corresponding output. We denote a continuous time signal by S of t, writing and assuming that t is a continuous time quantity or t is a continuous quantity. A discrete time signal is denoted by writing it as S of n, where this S of n stands for the sample at time n as well as the sequence of such samples. Okay. So, this is a continuous signal, this is a discrete signal. We will assume that this n is actually coming from time. Now, there is a relationship between these two signals, in the sense that if S of t satisfies certain conditions, then it is possible for us to represent this S of t not by measuring the value of S at all points t, but measuring the value of S at a certain time instant. Okay. In other words, I can go from the S of t representation to its discrete time version by a process known as sampling. Okay. I can go from S of t to S of n, provided that S of t satisfies certain conditions, namely that its bandwidth is limited to a certain range of frequencies. Then it is possible for me to sample fast enough so that S of n would be a accurate representation of S of t. I can go from S of n to S of t. So, this was the sampling process. I can go from S of n to S of t in what is called as the reconstruction of the signal. Okay. So, this relationship between sampling rate and the bandwidth, if S of t is band limited to b hertz, then I need to sample this one by at least twice the rate of b, is called as sampling theorem. So, sampling theorem tells us how to go from continuous domain to discrete domain. Although in this case we are dealing with only time signals, as I said, it is possible that the variable could be any other continuous quantity and the corresponding quantity will be discretized. Okay. So, you can go from continuous to discrete signals. Now, these representations of S of t or S of n are what is called as the time domain representations. Assuming that t and n represent the time, then these are called as the time domain representation. There is in fact an equivalent and much more widely used representation called as frequency domain representation. Okay. This is very useful because S of t, understanding S of t in time domain gives you one kind of a picture, but many engineers would prefer to understand these signals S of t and S of n by going into the frequency domain, where they can also think of translation in frequency, they can think of filtering a certain band. All these operations require us to visualize or to understand what happens to the signals in the frequency domain. The representation of S of t in its frequency domain can be obtained by carrying out what is called as a Fourier transform. Okay. If S of t is a real valued signal, that is at every point t corresponding S of t is real, then we call this S of t as a real valued signal. If such a real valued signal, for such a real valued signal we define the Fourier transform and we denote the Fourier transform by S of f. This S is capital, this S is small. Sometimes we will denote this by writing this as S tilde of f. In this case I am just going to use S of f itself. So, this S is a small case letter, capital S stands for the Fourier transform. So, for such a real valued signal, of course Fourier transform can also be defined for complex valued signals, but we will not be interested in the complex valued signals at least for some time now. So, S of t for a real valued signal will be S of f is equal to minus infinity to plus infinity. This is the integration over time by multiplying this S of t by a factor which is S of t e to the power minus j 2 pi f t. Okay. This is your Fourier transform representation. When S of t is real, then the Fourier transform turns out to be conjugate symmetric. That is, if S of t is real, then Fourier transform is conjugate symmetric. Okay. What do we mean by conjugate symmetric, or what do we mean by conjugate symmetry? It simply means that the magnitude of S of f is an even function and the phase of S of f, remember S of f is a complex number, right. So, for every frequency f you are going to get a complex number which is S of f, because you have a complex signal e to the power minus j 2 pi f t getting multiplied to S of t, right. So, this phase of S of f is odd symmetric. Okay. So, this is the meaning of conjugate symmetric, and this is how you can obtain the frequency domain representation of a signal. Okay. As an example, consider S of t to be an exponential function, say e to the power minus a t u of t. Okay. E to the power minus a t is an exponential function. If you were to simply plot that function, what you would see is that at t equal to 0 this would be 1 and then it would be decaying like this. Okay. However, t can also go negative because we did not say anything about t being positive or negative. So, what it means is that at t equal to minus infinity, this fellow would be at infinity, right. So, this is how e to the power minus a t is, and it turns out that such a signal cannot really have a Fourier transform, okay, because the integral will not converge, okay, in an ordinary sense. So, what we do is, or what we are mostly interested is, we want to know what is the Fourier transform of one side of the signal, right. To obtain that one side, we introduce this function called as the step function. This step function is defined by having its value equal to 0 for t less than 0 and it will be equal to 1 for t greater than 1, and at the middle, that is at t equal to 0, sometimes this is defined as having a value of half, which would be the average value to the left and average value to the right. Okay. So, this is your u of t. We will, when you look at this way, you will actually see that because the signal u of t is 0 for t less than 0, whatever may be the variations of e to the power minus a t be, that just gets vanished, or that just does not come at the output, and whatever variations after that would be multiplied by 1. Therefore, you have a exponential signal that is going like this, right. So, what you have done essentially is to remove all the values of e to the power minus a t function. So, if this is one function, so this function values has been removed when you multiply this one by u of t. Okay. What would be the Fourier transform of this? Well, to obtain the Fourier transform, let us go to the expression. So, S of f is given by e to the power minus at. Now, the integration can go only from 0 to infinity, right, because minus infinity to 0, the value of the function is 0. So, there is nothing to integrate. So, go from 0 to infinity, multiply this one by e to the power minus j 2 pi f t, because that is the definition. Then you combine this exponential powers, right, I mean the argument of the exponential function. Why can I do that? Because I know that exponential of theta 1 and exponential of theta 2 is actually exponential of theta 1 plus theta 2, right. So, this is the power law of the exponential functions. I can do that and modify the integrand as e to the power minus a plus j 2 pi f. T is a common variable, write this as dt. Carry out the integration. I know the integration of 0 to infinity e to the power minus a plus j 2 pi f into t dt is nothing but 1 by a plus j 2 pi f, right, e to the power minus a plus j 2 pi f into t within 0 to infinity. This is a small correction, of course, here, that there has to be a minus sign, because integral of e to the power a x will have 1 by a, and in this case a is negative, or maybe we should have used a different one. So, e to the power b x will have 1 by b times e to the power b x. Here we simply identify that b is negative, because you have e to the power minus some quantity times t. Okay. Because of this we have a minus sign here, and if you now look at what happens to this quantity inside, you will see very interesting thing. So, I have minus 1 plus j 2 pi f, and then I have e to the power minus a plus j 2 pi f times infinity minus e to the power minus a plus j 2 pi f into 0. This part should not represent us with any difficulty, because a into 0 will be 0, j 2 pi f into 0 will be 0. So, exponential to the power 0 is equal to 1. What about this quantity? Here I have e to the power minus a infinity, which would be e to the power minus infinity itself, because a being a positive quantity. I have assumed here, I have not told you specifically, but a must be a positive quantity. So, this e to the power minus a infinity could be positive, right. Then I also have e to the power j 2 pi f into infinity, right, or a minus j 2 pi f into infinity, right. This fellow will again become infinity, right. For f positive, this would be a positive infinity. For f negative, this would be approaching negative infinity. That is, when f goes to infinite, then this infinity in a positive sense, then this would be e to the power minus infinity, right. That is getting multiplied by e to the power minus infinity. This is a real signal, this is a complex signal, because there is a j sitting there. However, the product of this one will be equal to 0 as f goes towards infinity, right, positive infinity. What happens as f goes towards negative infinity? This quantity is actually not growing, but this is actually an oscillating signal. Okay. However, this oscillating signal is getting multiplied by e to the power minus a infinity. This would not change. Whether f goes to negative infinity or positive infinity, this e to the power minus a infinity is always going towards 0. However, if this had behaved in a very erratic way, then we would have had a problem in evaluating this expression. Luckily, e to the power minus j 2 pi f infinity will always have its maximum value to be equal to 1. Okay. Because of that, even as f goes towards infinity, this does not really matter to us, because this magnitude would always be equal to 1, and then that is getting multiplied by a 0. So, this quantity is actually equal to 0. So, regardless of whether f is approaching plus infinity or f is approaching minus infinity, this fellow is equal to 0, this is equal to 1, a minus sign here and a minus sign will cancel with each other, and you end up having the Fourier transform as 1 by a plus j 2 pi f. As we expect, S of f is complex, right. So, the Fourier transform is complex, but now if you look at the magnitude of S of f, you will see that the magnitude is given by 1 plus a square 2 pi f whole square under root, correct. So, this is the magnitude. Let me write down slightly correctly. and what you see, whether f is negative or f is positive, this S of f would always be equal to a positive quantity. In fact, if you were to graph this magnitude of S of f as a function of f, at f is equal to 0, you have a value of 1 by a, because a square and that square root will cancel. So, you have a value of 1 by a, and when f is going positive and when f is very large, this quantity 2 pi f square will become very large compared to a square, and that square will cancel, and then this would essentially go down to 0. Similarly, when f is going large in the negative value region, that is when f is going towards minus infinity, this fellow, this 2 pi f whole square will be much larger compared to a square, and then you can remove that, neglect this a square quantity, and then the square will go away. But because f is getting squared, even as f goes negative, this fellow will always go towards, this would be positive and this would be going towards 0. So, you can connect these two, and this would essentially be the way in which S of f would behave. Such a description, or rather when you square S of f, right. So, when you square this one, then the square root will go away. This wave or this function is widely used in lasers, to represent, and you can actually show that lasers will have such a characteristic, is called as a Lorentzian. Okay. So, this function is called as a Lorentzian. We will see this Lorentzian when we discuss the line width of a laser later. Okay. What you have to get from this equation is that magnitude of S of f is an even function, as you can very clearly see, it is an even function of f. But if you were to calculate the angle of S of f, you would be seeing that this would be negative, this would be odd symmetric. Why? Because I can represent this a plus j 2 pi f in terms of its magnitude and its phase, which I can write this as e to the power j theta, where theta is equal to tan inverse of 2 pi f by a, and because this 1 by e to the power j theta is there, this will go up and become e to the power minus j theta. So, the angle will be tan inverse of 2 pi f by a. So, this fellow will be e to the power minus j tan inverse of 2 pi f by a. When you look at this function, right, and if you start looking at the values of f, this would be negative. Did I get it all right? So, I hope that this would be okay. So, just you can put a small thing and find out this as an exercise. What you should be able to show is that this would be a odd function. So, for f positive it would be going in this way. So, for negative f it would be going this way, or maybe in this particular way. I am really not really concerned about which way it goes, but essentially to show that this has to be a odd function of f. Okay. So, what I was trying to tell you is that S of f for a real valued S of t, and certainly this e to the power minus a t u of t is a real valued signal. For this real valued signal, S of f turns out to be a complex, or it turns out to be a conjugate symmetric function. So, this conjugate symmetric implies that S of f magnitude is even symmetric and S of f is odd symmetric. Okay. So, this is what the Fourier transform representation of the signal S of t is. Now, why is this important for us? Well, let us look at one example here, or let us look at one system here, where I start with what is called as a pass band signal. What is pass band signal? Well, if you go back to this Fourier transform, where is the average frequency of this Fourier transform, or where is the Fourier transform centered at? It is centered at 0 hertz, correct? So, such signals are called as baseband signals. So, this e to the power minus a t u of t, whose Fourier transform is centered at f equal to 0, right? This is the Fourier domain. So, the Fourier transform is centered at 0 is called as a baseband signal, because much of its frequency content is located at f equal to 0, or the DC signals. However, there are situations when you consider signals whose center frequency is located at not 0 frequency, but at some very high frequency that is greater than 0. How can I obtain, or where do I find such signals? Well, whenever you modulate a signal, we have seen that after modulation the spectrum would essentially move towards the higher frequencies. Consider, for example, your double sideband suppressed carrier modulation. S of t is given by m of t into c of t. We know that c of t is cos 2 pi fct, and m of t is whatever the message signal m of t that you are sending. Let us assume that the signal m of t is baseband, indicating that m of f would be centered at 0 frequency. Okay. So, m of t is a baseband signal. What would be the Fourier representation of cos 2 pi fct? Well, we will not go into the details of the Fourier transform, there are some issues here, but the Fourier transform of this one is given by half delta f minus fc plus half delta f plus fc. Okay. This delta f is a function which is called as the impulse function, which is defined in a way which says that if delta of t is a impulse function, then delta of t is equal to 0 for t not equal to 0, and the area of delta of t will be equal to 1. We normally consider them to be a normalized to 1. So, what we are saying is that it will be 0 for t not equal to 0, and if you integrate this one, this would be equal to 1. An example of an impulse function would be a triangular function, okay, of width t and an amplitude of 1 by t, but as you start decreasing t, as you consider sequence of such functions where t goes off to 0, 1 by t goes grows and grows, and it would essentially start to look more and more like a, it would look like this. Eventually it would start to look like a impulse function. Okay. So, this is an example of an impulse function, except that in this case impulse function happens to be in the frequency domain, right. Now, when you find out what is the Fourier transform of s of t, you will see that this would be s of f, and it is given by m of f, right, convolved with half delta f minus fc plus half delta f plus fc. You might be wondering what this convolution is. Convolution operation is defined for in this manner. So, if I have two signals S1 of t and S2 of t, the convolution of S1 and S2 of t is denoted by this star and written as or evaluated as S1 of tau, S2 of t minus tau, and integrate over this variable d tau. Tau is a dummy variable. All you are doing is take the signal S1 of t and then take the signal S2 of t, invert it, and then keep delaying it. Okay. So, if S1 of t is this, right. So, if this is your S1 of t and this is your S2 of t, okay, all you are saying is that if you were to invert this S2 of t, okay, in order to, so if you flip this around, you will get this signal, and then you need to delay it. Okay. So, you are essentially going to get this signal. This needs to be multiplied pointwise to this S1 of t. So, you multiply these two signals and integrate. You keep doing this for every value of time shift t, and then you will essentially obtain the result of this integration. Okay. More details are of course available for you in the signals courses. Please refer to that. If you have forgotten, you can go back and read some signal and system textbook. You will be able to understand what convolution is, or you will be able to recall what convolution is. Okay. With that in mind, convolution operation can be performed in time domain, it can be performed in frequency domain. It turns out that these impulse functions have a very special property, that if I convolve any signal which is not an impulse, right, m of f convolved with delta of f minus fc, right, what I get is that it will be m of f minus fc. Okay. So, when I convolve them, I will get m of f minus fc, and why this is convolution in the frequency domain is because there is a Fourier transform theorem which tells us that multiplication in time domain is convolution in frequency domain. Okay. So, because of that, your double sideband suppressed carrier signal, which is m of t into c of t, can, the Fourier transform of that can be thought of as the convolution of m of the Fourier transform of m of t, which is m of f, and the Fourier transform c of t, which is this delta function, right. So, if you now look at this convolution, I am not proving any of this. So, if you look at this relationship and then apply it to this equation, which we will call as 1, then I can find the Fourier transform s of f as m of f minus fc, there is a half here, plus half m of f plus fc. What is this m of f minus fc and m of f plus fc? This is now, if you start with m of f, right. So, let us say this is my m of f, I am just plotting this one. If you start with this which is centered at 0 as it should for a baseband signal, m of f minus fc would correspond to a signal which has been shifted to the right. Okay. So, it has been shifted. So, let us say the value here is 1. So, this is 1 and let us say this fellow has a value of b and this is minus b. So, therefore, this becomes f c plus b, this is f c minus b. Okay. Similarly, so this is m of f minus f c, okay, and m of f plus f c would be a function which would be shifted to the left, which will now be centered at minus f c and will be at minus f c plus b minus f c minus b. Okay. When you combine these two, what you get is this s of f, when you also change the amplitude from 1 to half. So, you get 1 located at f c, the other spectral half is located at minus f c, this has a value half, this has a value half, this is your signal s of f. Okay. Now, such a signal which is centered not at 0 frequency, but centered at a different frequency f c, f c must be much larger than 0 hertz or the DC signal, is called a pass band signal. Pass band signals are encountered whenever you modulate your time domain baseband signal. So, when you look at the corresponding frequency domain, you will see that they are now centered at value f c. Okay. Now, for one of the things that has now happened is, if you have taken s of t as an original real valued signal, as you should obtain when you connect physical modulators, the signal that you are obtaining will be a real signal s of t. For such a signal s of t, the Fourier transform will show that it has components both in the positive frequency domain as well as in the negative frequency range, right. So, you have negative frequency domain. So, here all the frequencies are positive, here all the frequencies are negative. So, the corresponding s of f has values, non-zero values in both, but you can already see that this both copies are essentially identical, because the magnitude spectrum of these two are the same, and when you look at the phase spectrum, you will see that these two would also be identical. Okay, they would also be odd functions. So, the point here is that it kind of seems redundant to you have two copies. Okay. In fact, when you take a modulator in the electrical domain, what you will find is that if you start with a real valued signal s of t, which is a pass band signal, okay, the first operation that you will do is what is called as the down conversion operation. The result of a down conversion operation is a signal that is now centered at 0 frequency. You somehow have to make this signal which is centered at non-zero frequencies to be centered at the frequency f. Okay. This process of going from pass band to base band is called as down conversion. Now, there is a very important fact about down conversion that we have to understand. The way in which this down conversion we are going to do will result in not a real valued signal, but in a complex baseband signal. Okay. It will result in a complex baseband signal, or sometimes called as complex low pass signal. Okay. Complex low pass equivalent signal. These concepts are not only important in communication, they are also important in laser theory. So, if you spend some time understanding this, you will be able to understand and appreciate the topics in laser theory also very well. So, this is called as complex low pass equivalent signal or complex low pass equivalent representation, which will be obtained by down converting from pass band to baseband signals. Now, how do we do this down conversion? All I can think of is a very simple way. I already know one function which takes away all the negative variable values, right. So, if you recall this e to the power minus at signal here, we multiplied this e power minus at with this function u of t. U of t, what it did? It removed all components of e power minus at which when t was less than 0. Now, if I can do a unit step function in time, I can as well do a unit step function in frequency, right. So, what I have to do in order to eliminate all these components would be to multiply this one by a unit step function, okay, by a unit step function whose value will be equal to 1 for f greater than 0, and it would be equal to 0 for f less than 0, right. At f equal to 0, sometimes you can have this value as equal to half. So, when you do this, all these negative frequency components would vanish. after I multiply S of f by U of f, all these components are gone. What would be the corresponding spectrum? The spectrum is now having only components in the non-zero, only in the positive frequency domain, right. Now, if you look at that spectrum, that would be centered at Fc. Now I have to bring this Fc down to 0. What should I do? I have to translate this back in frequency, right. Here is where your couple of Fourier transform properties would help. If you take S of t, which has a Fourier transform S of f, and when you shift this one by a factor t0 to the right or to the left, depending on whether t0 is positive or negative, this would be equivalent of multiplying this Fourier transform by this phase factor e to the power minus j 2 pi f t0 into S of f. Similarly, if I start with S of t, which has a Fourier transform of S of f, and then if I consider S of f minus fc, then this would be equivalent of multiplying this by e to the power j 2 pi fc into S of t. So, multiplication of S of t by e to the power j 2 pi fct is equivalent of shifting the spectrum to the right, but I do not want to shift the spectrum to the right, I want to shift the spectrum to the left. So, to do that, I simply consider fc to be negative, right. So, if I consider fc to be negative, then I get S of f plus fc, and this will be a minus signal here. So, I have now identified two operations that I need to do. Start with a real valued S of t, which you would anyway receive. To obtain the complex low pass equivalent signal or the complex baseband signal from this, you multiply the Fourier transform of S of t, which is S of f, by the function U of f, right, and then in time domain you also multiply this one. So, this, let us call this as, let me just rewrite it in the block diagram way so that we can understand. So, S of t is coming in this way, that goes into filter whose transfer function phi of f is equal to U of f, and the output of this filter will be multiplied by e to the power minus j 2 pi fc t. Okay. What comes out will be the complex baseband or the complex low pass signal. In fact, there is a name to this particular output. Okay. Name to this output, it is called as analytic signal. Analytic signal will have its Fourier transform only in the positive frequency range. Okay. So, you have S of f here, right, and this after multiplying by U of f, you will have an analytic signal which will have components only at the positive frequency region, and once you multiply this one by e to the power minus j 2 pi fct, what you get is a complex low pass signal. Okay. Why should I get a complex low pass signal? Well, this signal by itself or this spectrum by itself will result in a complex valued signal, because the Fourier transform is now not symmetric. If the Fourier transform is not symmetric, it is not conjugate symmetric, then the corresponding time domain signal will be a complex signal. So, the analytic signal is necessarily a complex signal. This complex signal is now being multiplied by one more complex signal. It turns out that the overall signal that you are going to get will be a complex low pass signal. Okay. So, I hope this is understood. Once you have understood this low pass signal, then we can also understand, in the time domain expressions. We do not want to always think of the frequency domain in this case. It is necessary to also look at the time domain representations of these signals. To do that one, let us split this phi of f, which was the filter here, which was used for down conversion process, or rather this entire block is for down conversion process. Okay. So, this entire block is for down conversion process. This filter was removing all the negative frequency components, right. This was the U of f. I can split this signal U of f into two parts. I can write this as half plus j by 2 h of f, okay, because I want to discuss the filter properties of this portion. So, if I say h of f is equal to minus j signum function of f. Okay. What is this signum or the sine function? The sine function basically is positive when f is positive, its argument is positive. It would be negative when its argument is negative. So, if you plot h of f itself, you will see that h of f will be equal to minus j when f is greater than 0, it would be equal to plus j when f is less than 0, right. So, this u of f when f is greater than 0 will have half plus j by 2 into minus j but I know that minus j and plus j is 1. So, I get is this one equal to 1 when f is greater than 0. Now, when f is negative, for f negative this would be half plus j by 2, but this would also be equal to plus j here. So, this would be j and j is minus 1. So, 1 half minus 1 half will be equal to 0. So, I am all right. So, I can write u of f as 1 half plus j by 2 into h of f. So, that when f is greater than 0 I get 1, when f is less than 0 I get 0. And if you define further that signum function must be equal to 0 at f equal to 0, that would be the average of these two values, then u of f will be equal to half at f equal to 0, and we recover everything about u of f correctly. So, if I were to write down j of f, this would be minus j and this would be plus j as a function of f. Okay. Incidentally, if I take any signal and then pass it through this h of f. So, if I have now a filter which simply realizes this h of f and then pass this signal s of f through this h of f, output of this one will be minus j sine of f into s of f. Okay. This particular signal, this particular filter which produces this spectrum is called as a Hilbert transform. Okay. What is the significance of this Hilbert transform? You see here that if I were to take the magnitude of this, so let us call this output as S0 of f of this particular filter. So, if you look at the magnitude of S0 of f, I will see that the magnitude should be equal to magnitude of S of f itself, because there is nothing changing. The magnitude of minus j will be equal to 1 and sine will anyway be not, magnitude will always be equal to 1. So, the magnitude input of this filter magnitude is equal to the magnitude of the input. But look at what happens to the phase of S0 of f. The phase will be changed because you have a minus j here. Minus j is equivalent of e to the power minus j pi by 2, right, and sine function will be positive when s of f is positive, and when it would be negative when s of f is negative. This would be added to the phase of s of f. Okay. So, the total phase will actually be phase of s of f minus pi by 2. Okay. When f is positive, you will have to subtract minus pi by 2, and when f is negative, again you will have to subtract this minus pi by 2, right. So, all the frequency components of s of f, the phase of those frequency components are getting delayed by pi by 2. Okay. This is the action of Hilbert transformer. Sometimes that is why this is called as a phase shifter as well, okay, because it shifts all the frequency component phases by a value of pi by 2. Now, what is the significance of that? Well, if you denote the output in the time domain, the output of the filter in the time domain, you will see that that would be a complex signal which can be written as s hat of t. That is, if I take this minus signum function of f into s of f, that would correspondingly give me a complex number. So, I get s of f multiplied by u of f, but I know that u of f is nothing but half plus j by 2 into h of f. Okay. So, if I expand here, I get half s of f plus j by 2 s of f h of f, and h of f itself is given by sine function into f, right. If I now go to the time domain representation, this by taking the inverse Fourier transform, what I get here is half into s of f, which would be s of t, and this fellow will be a complex signal, right. This will be a complex signal which we will write by writing a cap over s. Okay. This is called as the Hilbert transform of the signal s of t. Okay. This would be the Hilbert transform of the signal s of t, and therefore, the signal that I am obtaining right after this or this is after the multiplication by u of f is called as the is the complex signal. This is called as the analytic signal. Okay. This analytic signal will have its Fourier components only in the positive frequency range. Okay. So, this is your signal half s of t plus j by 2 s hat of t. This we will denote by writing at s plus of t. Okay. This is not the completion. To this s plus of t, if I multiply by e to the power minus j 2 pi f c t, remember this is the second operation that I am supposed to do to convert the passband signal into a complex low pass equivalent signal. If I multiply this one, then what I get is the analytic signal S of t. Okay. This is given by, and if you recall what S plus of t is, S plus of t is half S of t plus j S hat of t, right, and then you have e to the power minus j 2 pi f c t. Sometimes you do not multiply by e power minus j 2 pi f c t, but rather multiply it by a square root of 2 into e to the power minus j 2 pi f c t. This is done so as to scale up. I have not done that one here, but in some texts and in some literature you will find that the multiplication portion will have a square root of 2 in the prefactor of e power minus j 2 pi f c t, just so that the energies of the complex envelope signal will be equal to the energy of the original passband signal. I have not done that one. Okay. Now, this is your S hat of t, called as the complex baseband signal, or sometimes called as the complex envelope. Okay. What is the significance of this complex envelope? Well, the significance of complex envelope is that you have S of t. So, let us write it down here itself. What would be the mathematical way of obtaining S of t? How do I obtain mathematically what would be S of t? In order to obtain that one, I need to simply remove this e power minus j 2 pi f c t. So, to remove that one, I should be multiplying this S of t by e to the power plus j 2 pi f c t. So, when I multiply here, this e to the power minus j 2 pi f c t and e to the power plus j 2 pi f c t will cancel. So, that is gone, and I still have this part to recover. This part can be recovered by writing this as the real part of it, right. So, if I take the real part of it, I simply obtain S of t. Of course, what I will obtain is half S of t. So, therefore, I need to multiply this one by a factor of 2. So, I can go from, this would be equal to S of t. So, I can go from S of t itself, I can go from S of t itself, which is a real valued signal. So, this fellow is a real valued passband signal. From this real valued passband signal, I can go to the complex envelope. Okay. I can go to the complex envelope, and then I can recover real passband signal from the complex envelope and vice versa. In practice, or in widespread use, you do not normally write down S of t as S of t plus j S hat of t. Rather than that, you write down this S hat S tilde of t, which is the complex envelope, as S I of t plus j S q of t, and call this S I of t as a in phase component and S q of t as the quadrature component. Whereas, I mean, what is that? S I of t is actually the real part of S tilde of t, and S q of t is the imaginary part of S tilde of t. To obtain this, substitute what is S tilde of t, the complex envelope. The complex envelope is, there is a half factor S of t plus j S hat of t times e to the power minus j 2 pi f c t. I am looking for the real part of this, which means that I have to expand this e to the power minus j 2 pi f c t and make this as cos 2 pi f c t minus j sin 2 pi f c t, multiplying S of t plus j S hat of t. Let us forget about this half factor for now. When I look for the real part of this, I see that this would be S of t cos 2 pi f c t. That is because S of t and cos 2 pi f c t would be the real number, S of t and minus j sin 2 pi f c t would be complex. So, therefore, they will not be coming in with me. S hat of t, j S hat of t cos 2 pi f c t will also be imaginary, therefore, that will also go away in this real operation. Plus j and minus j will be plus 1. So, I get plus S hat of t sin 2 pi f c t. So, there is a half here. This is equal to S I of t. This is the in phase component. What would be the imaginary component? I do not have to do any more here. I have already obtained the expansion here. I just have to pick the imaginary components. The imaginary components will be half S hat of t cos 2 pi f c t, and then there is a minus j S of t sin 2 pi f c t. Okay. So, this is your in phase component and this is your quadrature component. You can very well show that if I take S I of t plus j S q of t, I should be able to obtain S hat of t, because that would imply multiplying this S q of t by j here and that j will be there, but j into minus j will be plus, and then if you add them up clearly you will see that this would be equal to s hat of s tilde of t, which is the complex representation. Well, this is s tilde of t, but what about s of t? This is a complex envelope, but what about my real valued signal s of t? Can I recover it from this si plus j sq of t? Well, I can, because s of t is given by 2 times real part of the complex envelope being multiplied by e to the power minus j 2 pi f c t. So, if I were to just substitute for this s of s for s complex envelope here and write this as si of t plus j sq of t, and then write down this e to the power minus j 2 pi f c t, I will be able to obtain what is s of t. So, this would be si of t cos 2 pi f c t, right, si of t cos 2 pi f c t, and then j sq of t cos 2 pi f c t will go away, but what the other real part that you are going to get is j sq of t multiplied by minus j sin 2 pi f c t minus sq of t, there is a factor of 2 sitting here, times sin 2 pi f c t. Okay. The reason why I should get a minus sign here is because this is actually plus, right. I forgot to put a plus here, because s tilde of t or the complex envelope will have an e to the power minus j 2 pi f c t. To overcome that one, you will have e to the power plus j 2 pi f c t. So, therefore, this would be plus. So, this would come out, and what you get is s of t. Now, what is the significance of this all thing that we have discussed? Well, if you remember this IQ modulator that we discussed in the last module, we found that you can write down the output as some cos pi u I of t by 2 b pi multiplying cos 2 pi f c t or cos omega s t plus plus cos pi u q of t by 2 b pi multiplied by sin omega s t, right. So, those cos of pi u I of t by 2 b pi and cos of pi u q of t by 2 b pi are the in phase and quadrature components, okay, of the IQ modulator. These are the in phase and quadrature components. You might question that they do not look exactly like si of t and sq of t, because there is a cosine function there, but remember these are the outputs of the Mach center modulator. So, you need to operate them or bias them at the minimum transmission points and assume that ui of t is a small number. So, you can have this, you can remove all this cosine, and then all this pi by 2 b pi can be absorbed into a constant to obtain ui of t. Similarly, you have to bias it in such a way that you get a minus sign here. That can also be done by going to the other operating point and then remove this cos, remove this pi by 2 b pi, these are the constants, and you get a minus uq of t. The output of the IQ modulator was ui of t approximately plus j uq of t. This was multiplied by e to the power j omega s t. So, it is possible to go from this, it is actually what we have seen is that this IQ modulator is actually implementing the IQ representation of the signal s of t. So, by changing the in phase or the quadrature component, or by modulating the in phase and the quadrature component, it is possible for us to perform the IQ modulation. Okay. So, this is the significance of complex envelope. We will be meeting complex envelope, we will be meeting analytic signal when we discuss lasers and some of the properties of the lasers. So, we will close this module, right, with understanding of complex envelope. In the next module, we will take up some concepts from signal space which is required in order to understand digital communication fundamentals. Thank you.